After studying this module, you shall be able to know about logic of mathematical or computational methods adopted for determination of stability constants. Learn about curve fitting method and also about elimination method for determination of stability constant. In the general sense, the stability of a compound refers to the suitable conditions under which the compound can be stored over a long period of time. In reference to stability of complexes in solution, the terms which are specifically considered are thermodynamic stability and kinetic stability. Whenever we talk about the thermodynamic stability, we take into consideration equilibrium constants, which are a measure of heat released in the reaction and entropy change during the reaction. The greater the heat evolved in the reaction, more stable are the reaction products, and also greater is the increase in entropy during the reaction, more is the stability of the products. And by kinetic stability, one refers to speed with which transformation occurs leading to equilibrium. However, over here we are mainly concerned with the thermodynamic stability of the complex compound. Thermodynamic stability deals with the bond energy, stability constant and redox potential. The thermodynamic stability of a species is a measure of the extent to which the species will form or be transformed into other species under certain conditions when the system has reached equilibrium. Let us consider a case where metal ion M N plus combines with the ligand to form a complex MLN, where the equilibrium constant is equal to concentration of the complex in numerator upon in denominator concentration of the metal into concentration of ligand raised to the power of numerical coefficient. Thus, by knowing the concentration of metal, ligand and complex, the value of stability constant of the complex can be determined. The knowledge of stability constant is extensively employed in analytical chemistry, stereochemistry, biochemistry, solvent extraction, ion exchange processes, etc. There are many methodologies and approaches for computation of stability constants. That means stability constant is one such important parameter which we need to determine. And in this module, we will study curve fitting method and elimination method for determination of stability constants, starting with curve fitting method. Now, let us see what curve fitting method is all about. Curve fitting method is a process of constructing a mathematical function that has the best fit to a series of data points subjected to some constraints. It is a process of mathematical manipulation or approximation to fit the data on a particular geometric curve from which information about the chemical or mathematical phenomenon is comparatively easy to obtain. Let us see what this method is all about in a layman's language. Curve fitting simply is about capturing the trend in the data by assigning a single function across the entire range. For example, if we consider a straight line, we all know that a straight line is generally described by the equation y is equals to fx, that means it is a function of x which is represented as a of x plus b, that is a into x plus b. Now, the goal of curve fitting method is to identify the value of coefficients a and b respectively such that fx fits the data well. So, what we have is fx as a function of ax plus b, and if we look at the first plot which you all have on your screen, we find that all the points are connected point wise, but what we need is the best fit. So, what we have, we select a function which represents or best fits the entire data and we obtain a straight line with best fit. for the entire range. In order to understand curve fitting method for stability constant determination, let us take example of metal-ligand equilibria. As complexing processes are considered as occurring by a series of stages, thus it is possible to express the formation of stability constants, referring specially to the addition of ligands in a stepwise manner which is there on your screen. So, we have M plus L giving Ml with K1 as concentration of Ml in numerator upon in denominator product of concentration of metal and ligand. Now, applying law of mass action, what we obtain is the concentration of complex Ml in terms of equilibrium constant K1 into product of metal ion and ligand. Similarly, with addition of ligand at every stage, we obtain Ml2, Ml3 till Mln, whatever the case we are considering. Likewise, we obtain equilibrium constants for the respective reactions at each stages, and we obtain the expression for the complex in terms of equilibrium constant and respective reaction reactants. So, if we look at this table, the constants K1, K2, K3 till Kn are all stepwise stability constants. These stepwise stability constants are related to overall stability constants by the simple relation beta 1 is equals to K1, beta 2 is K1 into K2 and so on till beta n, which is product of K1 into K2 into K3 and so on till Kn. These equilibrium constants characterize the stability of complexes and are usually called as stability constants. The law of mass action is strictly valid only when activities of species is equal to the product of its concentration and the activity coefficient. One thing you need to remember over here is throughout we are using concentrations. However, the right term is effective concentration, which is activity, and it is expressed as product of activity coefficient gamma into concentration of the respective ion, that is C. So, we have A activity as product of gamma into C. Now, with this, if we look at the total metal ion concentration at any point in the reaction medium, we obtain the expression, that is Mt, which represents total metal ion concentration, is equal to the free metal ion M plus the metal ion which is consumed in making complex Ma plus metal ion used in formation of complex Ma2 till formation of complex Man. So, this gives me total metal ion concentration. On further simplification, I can simplify this expression of Mt concentration by substituting the expressions that we have obtained for the respective complexes in terms of equilibrium constants and the product of respective reactants. So, the expression that we obtain for Mt on substitution is equals to concentration of free metal ion plus beta 1 into concentration of metal ion into concentration of ligand and so on. Now, it is important to remember that the first term, which is concentration of free metal ion, it is nothing but beta naught into concentration of metal ion into concentration of ligand raised to the power 0. So, in all, this expression of total metal ion concentration simplifies to concentration of free metal ion into summation of beta I concentration of ligand to the power I, and this summation is carried over from I is equals to 0 to I is equals to n. Now, similarly, total concentration of ligand at any point of time in a reaction can be obtained by the similar equation. So, now the concentration of ligand, that is the total concentration of ligand At is equals to concentration of free ligand plus the ligand that has been used in formation of complex Ma, it is added to this free ligand concentration plus the concentration of ligand which has been used for formation of complex Ma2 into the coefficient 2. Since 1 mole of Man contains n moles of A, so over here we need to multiply every term with the number of ligand molecules taking part in complex formation. This equation is carried over till formation of Man. Now, on simplification we obtain the expression as At is equals to concentration of A plus beta 1 into concentration of M into concentration of A and so on till n into beta n into concentration of m into concentration of A raised to the power n. So, further this expression simplifies to AT is equals to concentration A plus concentration m into summation from I is equals to 1 till n I into beta I into concentration of ligand raised to the power I. With this we can calculate the average number of ligand molecules associated with metal ion, which is represented as n bar and is equal to ligand that has been used for complex formation upon total metal ion concentration. So, n bar becomes equals to AT minus concentration of free ligand upon MT. Substituting the values of AT and MT in this expression, we obtain n bar as, in numerator, concentration of A plus concentration of M into summation I into beta I into A to the power I minus concentration A, upon in denominator concentration M into summation I is equals to 0 to I is equals to n beta I into concentration of A raised to the power I. Now, this expression simplifies to n bar is equals to summation I beta I into concentration of A raised to the power I upon in denominator summation beta I into concentration of A raised to the power I. With this, let us consider two simple cases. Case number 1, where average number of ligand associated with metal ion, that is n bar is equals to 1. For such a case, the expression for n bar reduces to beta 1 concentration of A upon in denominator 1 plus beta 1 into concentration of A. Let us suppose that beta 1 into concentration A is equals to V. So, the n bar expression becomes n bar is equals to V upon 1 plus V. Now, on plotting log n bar versus log V for various ligand concentrations ranging from 10 to the power minus 3 to 10 to the power plus 3 gives the curve which is there on your screen. Now, this curve, that is the log n bar versus log V curve, is then fitted to experimental log n bar versus log concentration A curve on the same scale. At point of best fit, that is where log V turns 0, we obtain the value for beta 1. That is, at point of best fit, log V turns 0. So, log beta 1 becomes equal to minus log A or vice versa. Similarly, if we consider the next case where the average number of ligand associated with metal ion is equals to 2, there the expression for n bar becomes beta 1 into concentration A plus 2 beta 2 into concentration of A whole square upon in denominator 1 plus beta 1 into concentration A plus beta 2 into concentration A whole square. Again, over here, if we assume V as beta 1 A and we take logarithm on both sides, we obtain log V as log beta 1 plus log concentration A. Also, we assume over here that beta 2 upon beta 1 square is equals to capital P. With these two substitutions, the expression for n bar becomes V plus 2 beta 2 upon beta 1 square into concentration of A whole square into beta 1 square upon in denominator 1 plus V plus beta 2 upon beta 1 square into concentration A square into beta 1 square. This expression further simplifies to n bar is equals to V plus 2p concentration A square beta 1 square upon in denominator 1 plus V plus concentration of A square p into beta 1 square. So, we have n bar as V plus 2 PV square upon 1 plus V plus PV square. Again, over here log n bar versus log V is plotted, but these curves now correspond to an assumed value of P. The curves corresponding to different P values are then fitted to the experimental curve of log n bar versus log concentration A plot, and the one with best fit gives log beta 1 as minus log concentration A. Similar curve fitting methods have been developed for systems where n bar is greater than 3, but they are not very convenient to use because of increasing complexity. With this, we move to the next method, which is elimination method. In the elimination method, the overall equation of stability constant is divided into two parts. The first part associate with concentration of ligand and number average ligands participating in chemical reaction, while the second part deals with the values of stability constants. So, as a whole, variables and constants are separated, and by plotting graph between the variables, stability constants can be determined. The process is useful if only simultaneous equilibria are involved. That is, 1:2 or 2:1 complex is generally considered. For example, for a 1:2 metal ligand complex, the expression for n bar that we have obtained is beta 1 into concentration of A plus 2 beta 2 into concentration of A whole square upon in denominator 1 plus beta 1 into concentration A plus beta 2 into concentration A whole square. This on rearrangement gives us the expression n bar plus n bar into beta 1 into concentration A plus n bar into beta 2 into concentration of A whole square is equals to beta 1 into concentration A plus 2 beta 2 into concentration A whole square. This on simplification gives us the expression beta 1 into concentration A 1 minus n bar upon n bar plus beta 2 into concentration A whole square into 2 minus n bar upon n bar is equals to 1. This expression can be written as x p1 plus y p2 is equals to 1, where x and y are functions of n bar, concentration of ligand, and parameters p1 and p2 are related to stability constants. By dividing this equation with beta 1 into concentration A into 1 minus n bar upon n bar, we obtain the expression as 1 plus beta 2 into concentration A into 2 minus n bar divided by beta 1 into 1 minus n bar is equal to n bar upon beta 1 into concentration A into 1 minus n bar. This expression on simplification gives us the equation x is equals to beta 2 y plus beta 1, where x is equals to n bar upon 1 minus n bar into concentration A and y is equals to n bar minus 2 upon 1 minus n bar into concentration A. So, on plotting a graph between x and y for different values of ligand concentration and n bar, the stability constant beta 1 and beta 2 can be determined. With this, we come to the conclusions, the summary of this module. The knowledge of stability constant is extensively employed in analytical chemistry, stereochemistry, biochemistry, solvent extraction, ion exchange processes, and so on. In this module, we studied curve fitting method and elimination method for determination of stability constants. Curve fitting method is a process of constructing a mathematical function that has the best fit to a series of data points subjected to some constraints, whereas elimination method is a type of curve fitting method in which the variables and constants are separated and the values of unknowns are determined by best fit curve.